We'll now prove that the Hausdorff distance is a distance. Yeah, so I've spelled out the definition again in a single line to recall. The Hausdorff distance is between two closed and bounded sets, A1 and A2, is going to be the following. We look at distance between A1 and little a2, where a2 is in A, and maximize this over a2. So we have two given sets this way, one of them here and over here, and so this is the furthest point and its closest point is here. So we are maximizing this, and some point here is maybe this point is the farthest point and its closest point is here. So I take these quantities and I look at the furthest point in A2 from A1, and so it's drawn this way because this is the nearest point to this, and the other way around. So we are looking at these two sets, A1 to A2, and we are taking the larger of these two quantities, which is what I described in terms of engulfing last time. And our goal now is to prove that this is a metric. So first of all, of course, if A1 equals A2, then the distance between AA is what we have is 0. Okay, this is because each of these distances between A and a point in it is 0. We saw that already. Okay, but the main point to show is, suppose distance between A1 and A2 is 0 and these are closed and bounded. Okay, then this is the maximum of two quantities. Okay, so then we see that supremum of the distance between A1 A2 of A2 in A2 is 0. But what does this tell you? This tells you that therefore, well, this is supremum of non-negative numbers. So for all A2 in A2, distance of A1 and A2 is 0. This implies that A2 is actually in A1 because this is a closed set. Now A2 was arbitrary, so this is true for all A2 in A2. Okay, this is, in other words, A2 is contained in A1. Similarly, A1 is contained in A2. Okay, so we are done. So done because that is A1 equals A2. So this is a slightly non-trivial property, but it follows from the previous result. We saw that if you have a positive distance to a point not in a closed set from the closed set. Second is symmetry is clear. So Hausdorff defined the distance to make it symmetric. This is a general approach that is useful. If you start with something that is not symmetric, you can just make it symmetric, and then you have to study what happened in the process. It's not free, but you can analyze it. What takes a little more work is the triangle inequality. So suppose we fix A1, A2, A3. So fix A1, A2, A3, and these are closed bounded sets. Okay, and what we want to show is we want to show I won't state the lemma this way, so I'm just saying to show distance between A1, A3, and the distance here is the Hausdorff distance, is less than or equal to distance between A1, A2 plus distance Hausdorff between A2, A3. Okay, that's very well, but this is the maximum of two different quantities, as we saw. So we have to show what were those two quantities. I will say it in a picture. So here we have A1, we have A2 and A3. This is kind of the bad case. So it's distance between point little a3 and A1, the set A1. Okay, and the other way. And to show the maximum of two quantities is bounded above, we have to show each one of them is bounded above. That is in fact equivalent to showing the maximum is bounded above. And further, we'll spell out the details forward. Further, this distance itself is a supremum. It's a supremum over all A3s. I mean, then we are taking the supremum of distances over all A3s. So to show that this supremum is bounded above, we will have to show each of the quantities in that set is bounded above. Okay, so that's what we'll spell out in a lemma, and then we'll forward reason given this lemma. Okay, but we are going to throw a little more room into this. We'll give ourselves epsilon of room because we are dealing with suprema. and this is very useful when we are doing any kind of analysis. Okay, so we'll, instead of showing inequality for all epsilon greater than 0, we can say and for all A3 in A3, distance h of A1 and the point A3 is less than or equal to distance h of A1 A2 plus distance h of A2 A3 plus epsilon. Okay. Once we know this, we can get rid of the epsilon, of course, and we'll still get the inequality. You could even show less than strictly here. So how do we show this? Well, we have A3 and we are looking at its distance to A2. Okay, that means there is a point in A2 which attains this distance with an error of at most epsilon. But as usual, since we are going to have more than one term, we'll have to use epsilon by 2. Okay, so by definition of distance between the set A2 and A3, so that, remember, is a supremum, the infimum. So there exists A2 in A2 such that the distance between A2 and A3 is less than or equal to distance between the set A2 and A3 and with an error of epsilon by 2. Okay, so if we infimum need not be realized, but it's realized up to an arbitrarily small error. If this is a point, the right hand side is a little bigger than the infimum, and hence it may not be exactly realized, but there is a quantity better than that. But remember what the Hausdorff distance was. One of the terms of the Hausdorff distance was a supremum of these quantities over all A3. So this is less than or equal to dH of A2 A3 plus epsilon by 2. Okay, so if you recall, we can even see the definition again. We have a supremum of quantities. So here is A2 and A3, distance between A2 and A3 over all points. So any individual A3 is bounded above by the supremum. So by definition of A2 A3, there exists A2 in A2 such that this distance is less than or equal to this. Now similarly, we can have the same process with A1 and A2 instead, and starting with this point in A2, there exists A1 in A1 such that distance between A1 and A2 is less than or equal to the Hausdorff distance between these sets A1 A2 plus epsilon by 2. Therefore, the triangle inequality, if I apply it to this distance and this distance, you get that distance between A1 and A3 is less than or equal to the sum of the Hausdorff distances A1 A2 plus distance Hausdorff between A2 and A3 plus epsilon. Okay, but we know something about this. We know that what were we trying to prove? The Hausdorff distance between A1 and A3 is going to be bounded by, we are trying to just show the lemma here. We are showing the distance between A1 and A3. Sorry, this is not the Hausdorff distance. This is the distance of a point from a set. Okay, and so this, by definition, this is the infimum of quantities over all A1 in A1. So this is by definition less than or equal to distance between A1 and A3. So this is as claimed. Okay, now we have this. We know the rest is quite clear, as epsilon was arbitrary. Well, for all A3 and A3, we know that distance between A1 A3 is less than or equal to the sum of the two Hausdorff distances. So that epsilon of room we got was useful, but you can be thrown away. Okay, and now as for all A3 this is true, therefore supremum of the distance between A1 and A3 with the property that so supremum of this distance where A3 is in A3 is less than or equal to the sum of the Hausdorff distances. A2, A3. Now that we have both these inequalities, well, we are done now almost, because we can, so similarly, just to squeeze it into this line, we can reverse the role of A1 and A2. So if we look at distance between A3 and A1, and we look at the overall A1 in A1, this supremum is less than or equal to the same sum dH of A1 A2 plus dH of A2 A3, and the Hausdorff distance is the maximum of these two suprema. Okay, so therefore, to put it in this little corner, Hausdorff distance between A1 A3 is less than or equal to distance Hausdorff between A1 A2 plus Hausdorff distance between A2 A3. So this indeed is a correct definition discovered by Hausdorff, a very useful one, which tells you what is the different distance between closed sets in a metric space. Okay, closed and bounded sets in a metric space. When we study compactness, we'll see this is even nicer when we talk about compact sets, and it is actually attained in some sense. I mean, in an obvious sense that you have points which will actually give you one or the other of the maximums.